Okay, the next thing we're going to talk about is these two comparison tests. There's one called the direct comparison test, or the DCT, and one called the limit comparison test, which is called the LCT. The direct comparison test is basically saying you're going to take your series, whichever series you have to solve for, and compare it to another series. Then you have to think which series is bigger, and I think it'll make sense if I show you an example. You should decide which one's bigger, and if the bigger one converges, well then the little one must converge too, because, actually I think I'll just show you an example. I think it all makes sense. So let's say you have this series right here, n from 1 to infinity of n over 2n to the fourth plus n plus 1. So we can't factor the denominator, or I don't think you can. Yeah, you can't factor the denominator. You can't really do an nth term test because you're going to get 0, but that, once again, you can't test for convergence, so if it gets 0, you basically have to use another test. I don't want to do integral test. And the p-series test isn't going to work because there's all these other n's and stuff in here. So what we're going to do now is compare it. So what you're going to do is you want to compare it to something that has a similar high value. So we're going to compare this to this. And I like to write, I don't know if you have to do this, but I always do, compare to, and then I'm going to write the series I'm comparing to. In which case, well, the biggest one right here is this n to the fourth on the bottom. But there's an n on the top, so if this wasn't here, for example, this would just factor to like 1 over 2n to the third. So I'm going to compare this to 1 over n to the third. I'm sorry, 1 over 2n to the third. I wrote that wrong. Now, as we know before, you can pull out this 1/2 right here and get 1/2 1 over n to the third, and this, as we know, converges p-series p equals 3. Now we have to figure out, and this next part is going to determine whether or not you're going to use the direct comparison test and limit comparison test. As of right now, we're just doing, I know this one works with direct comparison, so I'll just show you. We're going to think, well, let's say we have these two functions, 1 over 2n to the third, and n over 2n to the fourth plus n plus 1. Which one is bigger? And what that means is basically which one has a higher numerator and a lower denominator in terms of n's. If this were to go to infinity, which one would go to infinity faster? Is basically the way we're saying this. Well, if we... in this one, you have more n's in the denominator. And because there's more n's in the there's another n in the denominator, you're going to be having a bigger denominator. And you might be thinking, well, if there's more n's in the denominator, but also more n's in the numerator, shouldn't they cancel out? Well, no, because the n's in the denominator here are being taken to the fourth power, and we're here they're only being taken to the third. So the n on top is kind of insignificant compared to the n to the fourth and the bottom. So you just think, this is a little thought, you have to think which one's bigger, which one would get to infinity faster, and that would be this one, because this one you're dividing by a bigger number, so this one's going to be smaller. So we can write that. Then I'm going to write this in series form, and that was definitely not a sigma, I don't know what that is. You're going to write this in sigma notation. Okay, and then this is going to be where we can check to see if this is going to work. How this idea works is that if the bigger one converges, something less than a converging value, like if this infinite series converges to some value, and this is less than that, then this must also converge, because infinity is bigger than any number it can converge to, and therefore this can't diverge, because if this diverged, then this would have to be bigger than this, which it isn't. So because this converges and it's bigger than this one, then this one also kind of has to converge. The same works the other way as diverging. Let's say we did this and we got diverging. That would have to be the smaller one, because if something diverges and that infinite series, and the infinite series that diverges and basically equals infinity, that's my infinity, and then there's a value that's bigger than that, well, that must also be infinity, because there's nothing bigger. The thing that's bigger than infinity is infinity, which means that must also diverge. So basically you can just say here, therefore, original series converges by DCT, direct comparison test, because you're directly comparing your series to another series, and for that reason you're using direct comparison tests. Okay, the other comparison test you're going to be using is one called the limit comparison test, and this is basically the next thing you're going to go to if you check and you get yours that converges, but it's smaller than your series, for example, because then that's not going to help you, because that means the other one could just converge to a bigger value, or it could equal infinity as well. So we're going to use something called the limit comparison test. The limit comparison test, there's probably a proof for this, but I don't know what it is, so you're just going to have to memorize what I got right here. Let's say right here we have bottom n equals 3 and the top equal infinity, and we have the function 4n plus 5 all over n minus 2. So the first thing you would think is, well, let's compare it to the n on the top is going to be to the 1/2 power, and if you divide that by n, that means you would get a 1/2 on the bottom. So let's compare it to this. Like that, n to the 1/2. Did I do that right? Yeah, n to the 1/2. As we know, this is a p-series. Diverges p equals 1/2. Now, because we know this diverges, let's look back here. If we put these two next to each other, well, this one has a bigger denominator, so this one's going to get to there faster, and therefore this one's bigger than that one. So you could write 1 over n to the 1/2 is greater than that thing. I don't want to write that. But the thing is that this one diverges, and so if this is smaller than something diverges, we don't know if that also diverges or if that is a value. And for that reason, we can't use direct comparison because there's not enough information, really. So we'll use this thing called limit comparison test. And basically what this means is that we're going to call this right here A, and we're going to call this B. With the limit comparison test, and once again, I don't really know why this is the case. This is just someone discovered this, that the limit as n goes to infinity of A sub n over B sub n, right? Now, if this is greater than 0, then that means that whatever you compared it to, if this diverges, then this diverges. If this converges, then this converges. So whatever you compared it to, if that diverges or converges, that's what your original series is. It's going to converge or diverge. Okay? So for this reason, we're going to then, I don't know why I'm erasing. I really don't know why, because I need to rewrite this, but it diverges. Then what we're going to do is we're going to take A sub n, which is this one. Which is going to be 4n plus 5 over n minus 2. And we're going to divide it by this, but because we're smart, we're just going to multiply by the reciprocal and get n to the 1/2 over, well, 1. And when you do this, and you take this to infinity, you're going to get the leading coefficients as 2 over 1, so this equals 2. 2 is greater than 0, and for that reason, because this diverges, then this must diverge. Therefore, original series diverges by LCT. So what did we learn? We learned that you're going to find a function to compare the series to and check if it's bigger or smaller. If the function converges and is bigger, or it diverges and is smaller, the one that you're comparing it to, that function, then you can say that it diverges or converges by DCT. And if that's not the case, then you can try LCT and see if you get something different than that. If you get something less than 0, then you can't really use this test. I guess we're going to have to try another.